Hey everybody, welcome back from spring break. Hope you all had a good one. As you know, there's homework due this evening. There's also a vitamin due this evening as well. TAs, vitamin due tonight, is that right? Or did we decide to say tomorrow? All right, so the vitamin that would have been due tonight can be due tomorrow. Give you a little more time to dig in on that. And then homework 5 will be passed out instantaneously, just about as we speak. So that kind of is the wrap-up on homeworks. Welcome back from break. For those of you who missed it last Thursday, hopefully you got to watch it on the internet. We had an excellent time, me and a few of my CS 186 friends, talking about text search. Today we'll conclude that and talk a bit about data visualization, because that is going to be the topic of your homework that you'll be starting this evening. So to review where we were last time, we had already talked about Boolean search and inverted files and how you can take documents and turn them into structured, essentially relational tables to support Boolean search. And at the end of that, we said it's awfully nice to be able to find all the documents that contain certain words, but what we'd really like to do is rank order the relevance of those documents to our search at the end of that query. How do we do that? And so what we went through last time was the classical content on ranking documents, and I'll review it briefly here, but this is just a review, so if you missed it last time, this is going to go very fast. The way we're going to think about documents is we're going to think about them as vectors of term occurrences. Remember, they're bags of words. Oh, no big markers? Nope. So a document is a big bag of words, and that means that you can represent it instead as a vector. So document can be something like this. Take all the words in the dictionary, etc. Your document is a vector as wide as the dictionary of counts. It has 6 occurrences of the word a and 0 occurrences of the word ah, and 0 occurrences of the word ah, maybe 1 occurrence of the word aardvark, and so on. And then when your document turns into a vector in a gazillion space, right? You can think of that vector as a vector in a high-dimensional space. And we can talk about documents being close or far from each other in this space. All right? The problem with that is that if you take that in its basic form, a document with lots of words will be really far from the origin, and a document with few words will be close to the origin. And the way we want to connect queries to documents is to treat queries as a document. So if you ask a query like this, I'm looking for documents that are relevant to the small aardvark. That itself is a document. It's got a vector which has only got 3 ones in it, 1 for aardvark, 1 for small, and 1 for the, and it's very close to the origin. So it won't necessarily be close to a document that says the small aardvark a million times, which is a shame because that's exactly the document you want. So what we're going to do is we're going to normalize so that short documents and long documents are close to each other if they have similar term occurrences in them. Okay? So we're going to normalize each dimension by its length. So you take the vector, however long it is, you divide all its components down by that length to get it as a point on the unit sphere. Now, every document is the same distance from the origin, distance 1, okay? And the distance between 2 documents can now be measured by looking at the angle between them from the origin on that ball, on that n-dimensional ball, all right? And that angle, the cosine of that angle can be computed, this is the law of cosines, by taking the 2 document vectors. So here's my query, which is another document vector, and just doing the dot product, multiplying this times this, adding in this times this, adding in this times this, and so on. All right, so that's the law of cosines. We can just take the dot product of those 2 vectors. All right, and that's going to be my distance metric now of these normalized vectors. All right? And so that's what I'm going to use as my proximity metric. That's the basic proximity metric, cosine similarity. Okay, that works okay, but the only thing is that the setup of the vector still isn't quite what we want. Yes? Is there like a official list of words, or is it like So you want to start with a static corpus of documents. All right, so assume it's 1975 when all this was invented, and the CIA gives to you all their documents. The first thing you do is you go through all of them and you find all the words. That's your dictionary. Right? And while you're generating these words, you can generate these vectors, and you can add slots to these vectors as you go. At the end, you need to turn them into efficient data structures, so you might do that in 2 passes. Now, if you're an internet company, you do this on a regular basis, right? You're constantly adding words to the dictionary. So you have to think about how you want to structure these documents. But we're going to see that actually in the next slide. These vectors are not actually going to be stored as vectors. Okay. So in order to do a little bit better than just cosine similarity, the thing is that counting term occurrences isn't that good because if a document has a term a lot, that probably means that term is especially important. And also, if there's a term that appears in lots of documents, it's probably not a very interesting term. Right? So the interesting terms are the rare words that you use all the time. I say database in this class more than is common parlance, right? This is probably a class about databases. Okay? Why? Because database isn't that common a word in the English language, and I say it all the time. Okay? So those 2 things, the frequency of the term in this document and the frequency of the term across the corpus, or rather 1 over that frequency because we want rare terms. So the inverse frequency of that term across the corpus are the things that we're going to actually want to stick in this vector. So for each document, we're actually going to store this TF times IDF, the term frequency, how often this term occurs in the document, which is what we had before in our vector. But we're going to multiply it by the inverse document frequency with a log in front of it for damping. So the total number of documents divided by the number of documents with this term. It's the inverse of the frequency of this term in the corpus. Multiply those 2 things together, stick those in your document vector instead of just the plain term frequencies, and that'll give you cosine similarity now in this somewhat more relevant space, okay, where term frequencies are being taken into account. So this is kind of plain Jane state of the art. Like this is what you would do if you don't have anything else. If there's no other structure other than terms and term frequency, this is a pretty good approach for document ranking. So we talked about this last time. Now, to your question of kind of how do you store these terms and these vectors, we're going to do it, again, through this notion of really just tables and joining tables together. And for making this painfully clear, we'll use an SQL notation. You would not implement this in an SQL database, to be clear. This is just for us to get a sense of what these tables look like. So in our we're going to add another table to our schema in addition to the inverted file. We'll keep information for each term. As we discover new terms, we'll add them to this table of what is the term and how many documents is it in. Every time you see a new document with that term, you update this table. All right, and this is the document frequency, or if you like, it's 1 over the inverse document frequency. Yeah? All right, and it's really a query over the inverted file table. As you populate this inverted file table, you can compute this from it. And it might be a good exercise for you to go back to the inverted file table and write down the SQL of what generates term info view. Okay? Here's the inverted file table. We're going to add another field to it, which is for every term document pair, we're going to store the TF-IDF right there in the row. So when you have that the word database appeared in the book database systems implementation, okay, we will store the TF-IDF. That is, how many times did the word occur in that book, and what's the IDF of that term? We'll store that in the row there. So every document will be stored with its doc term rank, the TF-IDF. And so now to do our query, this is the query we had before that gets Boolean results. It just takes the inverted file, and it self-joins it 3 times, if you remember correctly, right, on doc ID, right, with selections on term. And remember, those selections are little index lookups into a B tree that take us to the leaf where we have our postings lists. So just to draw this one more time, the inverted file is stored in a B tree, so indexed by term. And when we get to the bottom, if there's a term like Berkeley, we will associate with it a sorted list of doc IDs. It's in doc ID 4, doc ID 5, doc ID 11, doc ID 13, etc. And we'll do a similar thing for a term like database. Also sorted 6, 9, 11, 13. right? And we'll be able to do these lookups and then zipper together these lists with a merge join to find the docs that overlap. Right? This is all review from last time. So there's an example of a query that generates that query plan. And what we're going to do is we're going to layer on top of that simple Boolean search query our cosine similarity query, which is going to, from that Boolean result up there, it's going to multiply in the TF-IDF scores, the doc term ranks, if you want, for the tuples in the result of that. It's going to multiply those times the term ranks for the query. So if our query was the small aardvark, we have a term frequency of 1 for each of these, and document frequency for these can be looked up in that other table, right? So before we issue this query, we will look up the term info information for these guys. That will generate for this query the TF-IDF for the, small, and aardvark. And we'll pass them into the select list in this little box. Right? So the result of looking those things up is the Berkeley query term rank, the database query term rank, and the research query term rank. So sorry, the query we changed to was Berkeley database research. And that expression you see of the multiplication and addition is just the dot product, right? Question?
So when you order the magic points, are we getting the lowest ranking one or the highest ranking one?
So we want the highest. Yes, we want the highest things to be at the top. So it's descending order. And that's the magic ranking function. It's just the doc term frequency of the cosine similarity. Yeah. Okay, so it's not magic anymore. It's just math. Question?
The query term rank was all one for...
So the query term rank, and maybe I should blow this up, is actually computed in a separate query where you take the words in the search query. So this is a search query in the search box, right? You take each one of these words and you look it up in the table term info to get num docs, which is the document frequency. And then this is 1 over num docs for Berkeley. Right? This is 1 over num docs for database, 1 over num docs for research. And it's 1 because this query has each of these terms once. Term frequency is 1. Inverse document frequency is 1 over the thing you find there. And so what you're plugging into these expressions in this box, Berkeley query term rank is 1 over the document frequency of Berkeley. Make sense? Yep. So hopefully that demystifies the ranking to a large degree. All right, so the last thing we need to do is actually compute this. This is the actual query plan now. We're going to do this join of those postings lists that we look up at the bottoms of the B trees, right? And they're sorted by doc ID. And with the doc ID, we now have those doc term ranks handy. Right, we're going to store those in the postings list now as well in advance. So we can compute the sum of those terms as we scan these things. But the last step we have to do is that order by. We have to sort in descending order of the dot product, okay? So that's okay. So that's the query plan. And as we talked about last time, we're only going to do this for the matches in the index, for Berkeley, for database, and for research. We actually will not look at documents that don't have all three of those terms in this query plan. And we talked about last time that you could take this and you could union it with a Berkeley and database query. You could union it with a database and research query. You could union it with a Berkeley query, a database query, and a research query. And you could sort all of those if you wanted to. And then that would catch documents that contain subsets of these terms. Right? But right now it's a heuristic that we're just looking at documents that have all of the terms. All right? So you can augment this if you want. That's the fix. Merge join is fast. Computing the cosine while you're merge joining is easy. And then the last thing you have to do is sort. Okay. So that's not so bad unless your corpus is really, 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 really big. And then the question is, how do you parallelize this thing? All right. It's a query. It does have a sort. The sort result could be pretty big, especially if the corpus is big and the words are popular. So how are we going to parallelize this stuff? Well, there's a couple different ways we could do it. And this is where we left off last time. Questions before we parallelize? All right, so the parallelism decision is going to be driven by the most basic thing you have to decide when you're building a parallel database, which is where do you put the data? How do you partition up the data across the disks and across the machines? Right? And that's going to drive, in our case, the basic decision of what's going to be a faster way to build this search engine. And there's two obvious ways to partition these things. You can partition them by terms, or you can partition them by doc IDs. All right? And they lead to two different query plans. So if we partition it by doc IDs, think about what's happening. Here's a machine. It's got all doc IDs that hash to 14. What is that like? That's like a fraction of the web, if you want, or a fraction of the corpus. It's like a little subset of the data, and you could treat it almost as its own little search engine. Right? It's just not on all the documents. It's on a partition of the documents. And if you do that, then the way you're going to run this query is every one of these machines is running its query on its own little sub-corpus, getting its favorite answers for that subset of data. And then the top K that's going to happen across these at the end is, I have my top 10 docs. This machine has its top 10 docs. And this machine has its top 10 docs. And someone at the top can say, who's got the best one? And we all go, I do. Okay, right? And then everybody sends, say, 1 or 10, however, a batch of their top K to the central node, which then merge sorts them together and picks top K out of that. So this distributed top K thing can be done pretty naively, pretty efficiently. And you can have a multi-round version of this that's more efficient if you want. Because it might be that you don't want just the top 10, you want the top very many. And in that case, you may not want to fetch very many from each one of them. But I'll leave that as a optimization we won't talk about in class. Top K globally is certainly contained in each of the top K locally. Okay? So everybody can just send their top K to one place, and we do a global top K. So that's the partition by doc ID solution. The alternative is to partition by term, which means that this is a machine that has all terms that hash to 14. Berkeley, Aardvark, toilet paper, I don't know. Whatever terms hash to 14 are here. And here's another machine that has research and small and Cheerios, okay? And the thing is, to answer any given query, what we can do is we can do a parallel join between things that hash to this machine, things that hash to this machine, and we're going to merge join the B-tree lookups across these multiple machines, right? This actual merge join of these postings lists will happen in a parallel manner, right? Every machine will look up its keywords that it's got for the query, and then it will merge those keywords up in some parallel join algorithm, parallel merge algorithm, right? And parallel merge is not so different from top K. You just start getting ordered lists from each of the nodes and putting them together in one place. Or you can even build you can do them 2 at a time or 4 at a time. You can do multi-way merges. The other thing to note here is if you have a query like Berkeley database and research, you will take each one of these terms in this scheme, you will hash it, and you will figure out which node is responsible for it. So Berkeley's on node 14, database is on node 37, research is on node 142. And those are the only machines that will participate in this query. Right? So that's kind of nice. The rest of the cluster doesn't have to work on this query. Only the nodes that have data that's relevant for this query. So the work kind of partitions down to subsets of the nodes. All right, but we do have to do this parallel join. So which one of these is better? This was not clear to people up front. Maybe it's not clear to you. I'd be interested to hear people's suppositions about which one of these tends to work better. And generally, what are the pros and cons? Anybody got any cons on one of these things, where one of these looks like it's got a fatal flaw, or at least a flaw? Let me ask them. Oh, yeah, sure, go ahead.
So you said that for if you do it by turn, you only wake up like a certain subset of the cluster, right?
Right.
So if you have a couple terms that are a lot, and you only use it all a few times, like that happens, like you call a machine for all my queries, would that be an issue?
Excellent. All right, great. So imagine there are some terms that get queried very often, Justin and Bieber, right? Those are going to be some pretty hot machines. Right? The workload for those machines is going to be bigger than machines that don't have those terms, that have maybe less popular terms. So load balancing now becomes hard. You've got hot machines and cooler machines, or maybe you've got hot words and cool words, and you have to spread the the words out by how popular they are. So each node has an appropriately popular mix of words, right? And word popularity, it turns out, the internet, this wasn't even really known until the internet because people didn't ask these kinds of queries, but it became painfully obvious on the web. Word popularity, and actually this was known, it wasn't so empirically known. Word popularity has a distribution kind of like this. It's called a zip distribution. And it's usually described as 1 over 2 to the alpha for some alpha. These distributions it's also sometimes known as the 80-20 rule, that usually something like 80% of the frequency is in 20% of the values. So there's a few really popular things, and then 80% of the values have only 20% of the frequency. This is sometimes called the long tail. All right? This makes load balancing very hard. There aren't that many popular things, and they're way more popular than the unpopular things. So you got to get a lot of unpopular things to make up for one popular thing, and load balancing becomes very difficult. Okay, so this is one of the key difficulties with partitioning by term, is the Zipfian distribution of popularity of terms. If you partition by document, everybody is part of the Justin Bieber query, because everybody's got a Justin Bieber document somewhere. Every fraction of the internet has some Justin Bieber in it, no matter how you slice it. Right? Okay. So that's sharing the pain across the cluster in a very natural way that doesn't require crazy load balancing tricks. Okay. So that's definitely a con. One of the cons on the flip side of the partition by document is that if you ask a query over very rare terms, everybody's going to work on that too, even though there may only be two machines that have relevant data. Right? So you'll be issuing queries to nodes that maybe don't have anything to say to you, and that may happen on a somewhat frequent basis. But to be honest, looking something up in your index and finding out there's nothing there is not that bad in the grand scheme of things. You just provision, you slice up you get enough machines to answer all the queries, and you've solved that problem. So it's sort of a price you pay. So in general, we partition by doc ID to avoid these skew issues. Another nice thing about partitioning by doc ID, if you're an internet service, is that typically over time, you've got machines of different ages in your data center. Machines fail over the course of about 3 years, sort of median age. Many places will throw out machines after 3 years. So some of your machines will be faster and newer, and some of your machines will be slower and older. And what you can do is you can size the work that goes on a machine by just giving it a differently sized fraction of the doc ID space. And that just load balances itself just fine. Everybody answers the same number of queries, but they have less data to look at. Okay. On the flip side, if you partition by term, it's a little hard to predict how a given node's going to have to work. So handling things by partitioning by doc ID is quite nice. All right. So we can parallelize this pretty straightforward using parallel join algorithms and data partitioning just the way we thought about in our query processing. It's all a lot like relational. Note, of course, at the end, there's usually one more join. You get that rank-ordered list of doc IDs, and usually you're going to want to display something about those documents other than their IDs to the user. So you do have to join back to either the actual files or to some summaries of those files that contain snippets of text that are of interest. So there's one more join in here, which is docs, or some summary of the docs, where you go and you get things like snippets of text, and maybe the date it was crawled and the actual URL and title of the document, not just the doc ID. But you do that lazily. So you get your top 10, and then you go, okay, for this 10 documents that I'm going to display to the user, I will do 10 index lookups into the doc table. Right? So that's done through an index nested loops join because it pipelines. Remember, here's the doc IDs coming out of the subquery. And then the join algorithm into docs is going to be index nested loops join. Index nested loops. For every doc ID that comes up, you just do an index lookup and you send it to the output. 1, 2, 3, etc. You can stop at 10 and never do any more. Or if they say, I'd like to see another 10, you can lazily go look up 10 more. If you did a sort merge join, you'd have to sort the docs table first, which would be terrible, right? So you want a streaming join algorithm like index nested loops here that can lazily evaluate more answers as the user paginates through the answer set. Make sense? Okay. So you rank before the join with docs, and then the docs is essentially index nested loops join. Now this is actually parallel index nested loops join, so you actually have to issue a fetch to all the nodes to go fetch the matches to your lookup, right? It's distributed or parallel index nested loops join. Every lookup has to go to the relevant nodes. Or you can replicate the docs table everywhere. That's another option. Then it's always local. All right. So that's how you implement TF-IDF rank search. Pretty good. It's all traditional relational databases. So we thought we were in a totally different field of text search, but really at the end of the day, it's joins and sorts and a bunch of metadata that you store as data about documents. One of the things we said was very different about text search was that there wasn't a correct answer. Right? Google sometimes is better than Bing. Bing is sometimes better than Google. What does that mean? How do you decide that something's better or worse? How does an engineering team decide what's better or worse? Well, there are some abstract metrics, and then there's some things you can do in the real world. But an abstract metric is usually defined in terms of precision and recall. And the colors here make this rather hard to read. I apologize. But the Boolean search answer is well defined, right? It's the set of all documents that contain all the terms. The ranked ordered metric, the thing is that people don't usually page through all the answers. If there's 10 million answers, you don't page through all of them. So the question is, if I look at only the top K, how well did this engine do? So the two common metrics are precision and recall. In that top K, the precision is defined as the size of what should have been the top K answers by some notion of should have. All right? So assume there's an oracle that says what the best K really are. Intersect with the K you actually retrieved divided by the K you actually... Sorry, I didn't say that right. Suppose that there's a set of correct answers of some size called correct. Okay? And then suppose there's the K we retrieved. All right? What's the intersection of correct intersect retrieved divided by size of retrieved? All right? So then might have been that there were only 5 right answers and I gave you 10, the top 10 that I found. All right? So then in that case, the intersection would just be maybe would be 5 or smaller, divided by the number you retrieved is 10. So how precise or sloppy was the answer you gave me? And then recall is the percentage of answers divided by the correct number of answers. So another way to think about it is precision is the percentage of the answers that are actually correct. Recall is the percentage of the correct answers that you actually found. So precision is how much sloppy stuff you gave me. Recall is how much of the good stuff you actually found. All right? And both of those things matter, so people usually measure both. And you can usually you can usually be good at one and awful at the other without too much work. The goal is to be good at both. Okay? Now, in the real world, actually, oftentimes the way you try to estimate this, you don't actually know what correct is, right? No one's going to actually tell you, if you're an engineer at Google, what the right answer was to every query they ever got asked. So instead what you do is you do user click-through as a proxy for what was correct. If the user clicks on the first one and then comes back and clicks on the second one, then the first one probably wasn't right. And then the second one maybe was if they stopped there, or maybe they just got bored. All right, but you come up with a model for user click-through as a proxy for correctness. And you get to run that experiment 1 billion times a day is the nice thing to tune up your engine. Right? And you can try out different rankings and compare across them, because if people keep asking the same kinds of queries all day long, you'll tend to get lots of experiments. So one of the things I'll tell you about web search, and I wish I knew this firsthand and I don't, but I know people who do, is that search engines are as good as they are because they've been tuning them for a decade now. Right? And they've been auto-tuned for a decade based on a workload of users and a workload of documents. And for you to walk off the Berkeley campus and try to build a new search engine is nigh impossible, because the ramp of learning you would have to do to get all the tuning parameters and forget about even the algorithms and the tricks, just the parameterization of those algorithms and tricks is phenomenal. The amount of auto-tuning that happens just through usage of these things is amazing, because they get used in such volume. So. All right. Sometimes you want to query things not just as a bag of words, but you're interested in phrases. And we got a sniff of this idea earlier, but here's for old people, even older than me, a query you might ask if you're into bands from the 60s and 70s is the Who. I want to find information about the Who. All right, well, if you take that query on face value, you're going to get documents that contain the word the and documents that contain the word who, and there's a lot of documents like that, and very few of them are about the British band. Right? So there would be a bazillion matches. Our previous query plan is just going to look at term frequencies. The and who probably appear pretty often in many documents. And the inverse document frequencies for these are both terrible. Like the appears all over the place, and so does who. So what we're really looking for is we want to find the next to who. That's unusual. In fact, it's very unusual. That's why they named the band that, right? It's like, what? The who? Right? That was the whole idea. So one way to do this is you can take all two-word runs in all documents and index those. Those are called bigrams. Okay? So if we did that, then the who would actually have a pretty small inverse document frequency, or a pretty large inverse document frequency, a pretty small document frequency, right? That pairing of words is not that common. It doesn't occur except when you're talking about the band, basically, right? So that's one thing you can do. You can generalize this to n-grams, and most search engines will do this. And then when you're doing a search and you get a query like Berkeley database research, you might take n-grams of the query as well. So you'll search for Berkeley, you'll search for database, you'll search for research, you'll search for Berkeley database, you'll search for database research, right? And then the answers to all those things are in the soup when you do your ranking, right? And it's really just a matter of populating the initial indexes with bigrams in addition to unigrams. But the schema doesn't change, and the queries don't even change. Okay? More generally, you don't have to do things that are next to each other. You could do things that are a few words apart if you wanted to. So you could get the freaking who would also maybe work, right? That'd be fine. So you can try to add a position field to the inverted index and use this proximity to boost the rank. We talked a little bit about this kind of stuff. Here's some other tricks that people do with ranking. These are common, actually. They happen all the time. So query expansion. This may be visible in your browser, or it may not be, where you type in a bunch of terms, and before we issue the query to the technology we just looked at, some clustering algorithm says, hey, people who ask about these two things also ask about a few other things. I'm going to add them to your query silently so that we get documents that maybe have those other things and not the things you asked for. So I don't know if oftentimes you've probably done searches where there's some documents that don't hit on any of your search terms, but turn out to be kind of relevant. Right? So that's one way that this happens. Right? So you can expand or modify people's queries. You can fix misspellings, and we talked about this in a previous lecture. You can use q-grams of letters instead of n-grams of words. Right? So you can index things on these trigrams of letters. You can also do document expansion. Eric Brewer, when he built the Inktomy engine, which was one of the biggest internet search engines in the late 90s, early 2000s, talked about a lot of times all they would do with documents is they would run the document through a classifier, and then the classifier would say, hey, you know what, this looks like Japanese, and they would just put the English word Japanese into the document before they indexed it. Or if you like, they added a term to the table doc ID, term ID that had this keyword Japanese. And then if you typed in a query that appeared to be in Japanese, they would add that to your query too. And then sort of for free, they were doing language search, right? And you could do that with anything. You could do, gee, you're using dirty words, so we'll let you look at the adult documents. But if you're not using dirty words, then we won't return the adult documents. The only thing you need to do is just put a tag on a document that says adult or not. Right? Those classifiers have to be good, but the actual infrastructure for how do you partition the data so that you catch all these things is just text search. Just make up some funny terms. Obviously, you wouldn't use the word Japanese. You'd use some hash-encoded version of it so it was a rare term. Right? So you can do that. And then the other thing you want to do on the internet, and probably in regular documents too, is that not all terms are actually occurring in the same way in every place. So sometimes things are at the very top of a document in big, bold letters. Those are probably pretty important for that document. So you might give them an extra term frequency, even though they're there only once. They're really big, they're really bold, and they're at the top of the document. So let's call that worth 10 times. Right? So you can play games like that to boost the significance of occurrences of terms. And all these things are done by just tweaking the input to this algorithm, not tweaking the algorithm. Okay? All right. So the thing that happened in the 2000s that got really exciting, I think, that was more than just 70s era technology, was that the web had hyperlinks, right? And no one had thought about taking advantage of them in web search till the PageRank guys at Google did it. And so this was suddenly, I shouldn't say no one, actually. There was John Kleinberg, who's at Cornell, and people at IBM had one at the same time called Clever. That was arguably even cleverer. But those two things came out at about the same time. And the idea that a graph contains information that could be used to help us search was quite new at the time, although the basic mathematics behind it is like as old as the hills. All right. But on the web, there's more information than just the text. There's the hyperlinks. And then there's these ideas, which actually were from the 60s and 70s, about social network theory, that, how do you find out, say, who's an influential scientist in a scientific community based on who cited whose papers? This is where a lot of social network theory kind of came up. More generally, how do you influence people? You want to find people in the network who are influencers, and they will influence other people. So it's used a lot in marketing now and things like that. So the intuition, and PageRank is a very simple algorithm to describe, so it became kind of popular to describe. The intuition is something like this. If you're an important person or page, and you point to me, well, then I'm an important person. Okay? The IBM one was a little more sophisticated. It would try to differentiate between what was called a hub and what was called an authority. A hub was just somebody who had lots of links to authorities. An authority was someone who had lots of inbound links to them. So it was directional. Right? PageRank is a little less directional, but that's fine. So let's just go with the PageRank one. If I'm important and I point to you, then you're important. Well, that's a recursive definition. Okay? So how do we know I'm important? You got to bootstrap somewhere. So it's just a recursive computation. Everybody starts equally important, weight 1.0. And then what you do is you iteratively share your weight on your outbound links in rounds. So we start out, everybody's 1.0. We take a full pass of the graph, and I take my 1.0 and I give little pieces of it to all of my outbound neighbors. So I have 3 neighbors. They each get a third of my weight. And I, of course, get all the inbound weights from my neighbors. Now, if one of my neighbors is really gregarious and points to a lot of people, I don't get much from them. Right? But if one of my neighbors has very few people they point to, I get a lot from them. And this propagates. And what happens over time is that nodes that are sort of central to the graph will accrue lots of this weight. And that's called the page rank of the node. Okay? And it's a global property. It has nothing to do with the documents. It has nothing to do with the content of the documents at all. So the page rank of a document is just something you compute through this algorithm, and you can stick it into your relevance ranking. So after you compute the page rank, you can just shove it into your doc term rank and all that other stuff and use it in your sorting function. It's just this document is this awesome because of its page rank. All right. No, you probably wouldn't have guessed. I certainly didn't. But the PageRank is actually a sort of naive approximation algorithm for computing the first eigenvector of the adjacency matrix of the graph. She's like, well, okay. I didn't know that. So these eigenvector things are supposed to tell you, what are the interesting things in a matrix, right? What are the interesting weighted sums of the matrix? Well, what's the adjacency of a graph, right? A graph, the adjacency matrix of a graph is nodes along one axis. 1, 2, 3, 4, 5, etc. Nodes along the other axis, right? 1, 2, 3, 4, 5, etc. And, there's ones and zeros in here for where there's an edge. And if you wanted to compute the eigenvalues of this graph, that's a way to do it, right? So they actually, so that's pretty cool. And there's other ways to compute the eigenvalues than this PageRank algorithm, but... So that just gives you a flavor. I'm not going to test you on this stuff, but this gives you a flavor of how you can use graph topology to help you get better ranking. And PageRank sure seems to help. And you probably don't know this, but in the early days of Google, that was their only ranking metric. They didn't look at the content at all when it was a Stanford research project. And actually, they would go do demos at little National Science Foundation meetings I was at. Like, we have this new search engine called Google. And we're like, why would you call it Google? And they would just search for stuff, and on a lot of things it did really well without knowing anything about what was in the documents. And they loved to do queries like Stanford, and they would get lots of good stuff about Stanford, right? I shouldn't say they knew nothing about it, because they had to have some keywords in there somewhere. But the ranking, the Boolean rankings, would be based only on PageRank. So they'd do the Boolean search and then rank by PageRank, and they'd do great. They'd have the most interesting pages about Stanford would come up first, like the university homepage and so on. So pretty cool. But now, of course, it's only a piece of what Google Corporation uses in its search. And rumor says that other factors matter as much or more than PageRank. So things like anchor text. What are the labels on the links that point into you? You should copy those into your document. So if someone points to your homepage and in their link they have anchor text that says genius, then what you do is you take that and you copy it into your homepage when you put it in the search index, and now you're a genius, right? So So you'll come up when people search for Genius. So anchor text turns out to be really important, and it's not captured by PageRank. Things like what's a title, what's bold, all these things. All this tweaking matters as much or more than PageRank. But PageRank is very interesting. All right. So here's some random notes from the real world of web search that I learned from my friends. So I can't claim to ever have worked at a web search company. I've worked at a bunch of different companies, but never at a web search company. So the first thing to know, and this was, I think you were alluding to this question, the vector length, the dictionary of terms on the web is staggeringly large and way bigger than any language ever known to man. So all numerals you can imagine are somewhere on a web page, right? So, and people like to search by them because they're things like serial numbers, right? I took my car to the shop this week, and it came back, and there was a little part on the dash, a little piece of plastic. I was like, what the heck is this? And I showed it to the mechanic. He said, I have no idea what this is, but it had a little number stamped on it. We're like, cool, we'll just Google it, right? People do that all the time. Right? So all the numbers in the world. Any string that's ever been put into any piece of software, all right? This is actually from a previous year's CS186 homework. Every misspelling that anyone's ever typed. There's all kinds of languages. Those all get indexed. So those are all interesting. Another interesting thing is web spam. So how do you protect against web spam? Well, what is web spam exactly? It's actually search engine optimization is what it's called now. You can pay somebody for this, right? But it's how do you get Google to rank you artificially high? Or how do you make Google look stupid? How do you do it? Well, it depends on the ranking function. So think about how you would spam TF-IDF. Suppose that you wanted to make Stanford look really bad on the internet. How would you spam the word Stanford? Well, it's pretty easy, actually. Right? Get a document with really high term frequency for the term Stanford, and then have it say what you want. Right? Another version of this is suppose you want your document. This used to happen all the time in the 90s. You want your document to come high ranked in searches by other people. Like randomly you want your document to show up in people's searches because you're selling whatever you're selling, right? Oh yeah. So this is a trick generally. If you want to have a whole bunch of junk on your web page and you don't want people to see it, you just color it the same as the background. I think actually the search engines are smart enough now to filter this out. But the flip version of this is, people used to say, I'm selling bananas on the internet, but what I'm going to do is I'm going to put the things that are most searched for on the internet in my document in white text on white background. So Justin Bieber, Justin Bieber, Justin Bieber, Justin Bieber, Justin Bieber, naked girls, and then buy my bananas, they're really cheap, would show up in everybody's searches. All right, but how do you spam PageRank? It's spam proof, yeah? There's apparently some famous interview with Sergey Brin where he assured you that Google was now spam proof, which he had to take back later on. Yeah.
Couldn't you then make a bunch of websites that each point to each other?
All right, so here's a good idea. You could make a bunch of web pages or websites and have them be deeply interconnected to increase each other's ranks. How would you make a bunch of websites programmatically? Well, you could write like a Django server or something, right, that keeps generating new page IDs with links so that when the crawler it generates a page with a link to a page that doesn't exist yet, and if a crawler follows that page, then your Django server generates a new page to a link to another thing, and all those pages point to me, right? So you can do stuff like that. So they have to be able to work against that as well. All right, so you can web spam, there's many different ways to do it. You can do it with the topology, you can do it with the content, etc. On the flip side, some real-world stuff makes life easier. Like terms and queries are Zipfian, we know, but that means caching works great. Because everybody asks the Justin Bieber question, it's already been answered a bazillion times. So we can just cache the answer. We don't actually run that query that often. Right? So that makes life very good. If queries were truly uniform random, there'd be a lot more work to do. Queries are usually little. All right? That means that index lookups as a key part of our algorithms is fine. If you tended to paste into Google like the phone book as your query, it'd be a drag, but people don't do that. All right? And then, users don't usually care if the answer is all that right. They'd like it to be right most of the time. They don't really mind if the answer is different, on their handheld at the same time they're looking at their laptop. That's okay. There's a pretty famous story, early days of the internet, Inc2Me. So it was a Berkeley research project turned into world's biggest search engine. Originally, their offices were in Berkeley. And they had indexed the entire web and brought it to Berkeley. But Berkeley real estate's pretty expensive, and they were a very big company. They were growing, and they leased space down in Foster City. So one day, they turned off half of the machines in Berkeley and put them in a truck and drove them to Foster City, turned them back on, did a DNS switch so all the traffic got routed to Foster City, turned off all the machines in Berkeley, brought them and plugged them into Foster City. So there was this period of time where the Ink2Me search engine was missing half the web. And kind of nobody really noticed. Or they didn't get a lot of complaints. And that was okay. So fault tolerance and things about dealing with failure are much, much more forgiving in this environment than like when you're doing business and when you're trying to transact money. Although there's a lot of ways you can be fault tolerant there too. Okay, obviously these have become the world's largest advertising platforms. I mean, compute farms, right? Google runs more machines than I think anybody ever. Facebook's probably close, and it's not a search engine primarily, but really big. And there's a whole science and engineering culture around that's developed in your lifetime and less on how you run these kinds of compute farms. It's a whole new thing that came up in computer science in the last 10 and 15 years. And honestly, the only people who really know it are the people who are doing it. So I could teach you some of the principles that they use, many of which are classical computer science in, say, a distributed systems course, and some of them we'll learn here in a database class. But some of this stuff is really only well known at Amazon, Google, Facebook, and about 4 other companies, which is kind of cool. It also means that every decision they make is relevant to only them, because no one else runs at that scale. We've talked about this before, right? There's like this big 6 or 7 companies that are engineering for a really weirdly large scale point, which is all people on the planet, and they make decisions that may be irrational for other normal computing places where you might do something more sophisticated. So, all right. In the slides, you can have some fun reading about how to build a web crawler. I will not cover this now. We may come back to it later in the semester for fun, but I want to move on and talk about data visualization. So we're going to skip this stuff. And by the way, in terms of exams and quizzes and things like that, you won't be quizzed on PageRank or any of this stuff at the end here, but you will be expected to know about cosine similarity, TF-IDF, and Boolean search. Okay. Cool. And you'll get a vitamin on that stuff to reinforce it this week. Okay, why doesn't everybody take a stretch? All right. So I apologize. I'm a little under the weather. Apologize for coughing at you. Oh, no. Yeah, my fonts got... Oh, no, they're fine. It's just showing footing. All right. So I want to talk about data visualization, partly because it's really interesting, partly because you have a homework on it, but you mostly have a homework on it because I think it's really interesting. And there's a lot of resonance with things you learn about database systems when you talk about data visualization. And so it seems apropos to add this to the class this year. It's the first time we're covering this material in 186. And it's going to be exercised in your homework. It may not be all that particularly testable on a test. We'll have to see about that. But it's a really broad field in its scope of concern, so in its intellectual scope. And it's growing super fast. So we have an entire graduate course you can take on data visualization, and I certainly will not cover nearly the breadth of topics that they cover there. There are many mature commercial products and startups in this space, companies like Tableau and ClickTech. There's some very popular open source packages like D3 and processing. There's entire academic conferences. There's even popular coffee table books like Edward Tufte's books on data visualization are especially popular. He has a gallery in Manhattan where you can go see his data visualizations. Right? They don't have this for database internals. So there's an aesthetics to it that's broadly appealing. And then this is March 27th this year, this Sunday, 2 days ago. There's an article in the New York Times about learning to see data, about how these medical researchers brought in an artist to help them look at their data. And then one of the authors of D3, a guy named Mike Bostock, actually is a reporter at the New York Times. he has his own byline. He wrote D3.js. He wrote a data visualization toolkit you guys will work with. And he produces interactive online visualizations for the New York Times as a form of journalism. So it's like a popular medium. Think of data as a medium like music or text or film, okay? That's what's happening. So it's very exciting if you're a data person, right? It's exciting times to see a guy who's essentially a software engineer and data guy with a byline in the New York Times. He took a significant pay cut for that job, is my suspicion. He used to work at Square. Okay, so what are we going to talk about data visualization 186? Well, we're going to focus more on how you build visualizations than what visualizations are good ones to build, right? So for example, one of the things that my colleagues in data visualization study is perceptual, human perception about, say, color. So if you're building a bar chart and you're building like a heat map of, say, crime in the U.S., and you want, places with lots of crime to be one color and places with less crime to be another color. What color palette should you use? Well, probably one that people can well differentiate, all the gradations. And it turns out that that's not as simple as just going up and down the hex scale of colors, because our eyes and our brains don't process color linearly. So you have to do lots of user studies to figure out what colors are good for different people. And it's fascinating stuff. I'm not going to go into it, but it goes back to like cultural differences, not only perceptual differences. Different cultures have been shown to perceive color differently based on how they name their colors. It's quite interesting. So there's things about perception, there's things about aesthetics, and so on. We're going to specify we're going to worry about how you build these things, and particularly how to elegantly specify data visualizations. So the key observation we'll start with. What is a data visualization? It's a mapping. It's a mapping from data values to graphical objects. When we're visualizing data, all we're really doing is transforming its values into values that we know how to render on a screen. So it's a mapping problem. Okay. And the second observation is how do you best specify data mappings? Well, they're really just queries. Okay? And visualization languages have sort of grown into this realization. They started out being like programming languages, and they've become much more like declarative query languages over time. All right? With all the benefits that you get from declarativity, like we learned for databases, you get much more concise specifications of your visualizations. You have languages that are better fit to the task of data than general-purpose programming languages. The things that people write down are easy to analyze and understand and then reuse in different ways. All right, so a lot of these benefits on specifying data visualizations that community has been developing are a lot like databases evolved from, say, the 60s to the 80s in terms of going from programmatic APIs to declarative languages like SQL. Now, the Viz people did this much more recently. This all happened in the last 10 to 15 years, I would say. And they've moved up the learning curve a lot more quickly, obviously, because we know a lot more now than we did in the 60s and 70s. And they stole ideas from databases liberally. We're going to look at two flavors of languages in our lecture. You will work with the first of these. So D3.js is a kind of somewhere between imperative and algebraic language. It's very deeply embedded in JavaScript and the web, because that's where a lot of visualization needs to happen. And it's extremely popular in the JavaScript community. It's one of the top 10 most popular projects on GitHub, as last check, above Linux, for example. So very, very popular project. The second one we'll talk about is Vega.js, which is a higher-level language that actually compiles down to D3. It's more declarative, but it's also more restricted. It doesn't let you do as much, so it makes a trade-off between conciseness and expressivity. Vega.js is actually typical of a number of high-level data visualization languages, and that's kind of the reason I'm showing it to you, is there's a family of languages that all kind of smell like Vega. Okay, so D3, let's start with D3, and this is what you're going to need to program in for your homework. D3 stands for Data-Driven Documents. So interestingly, there's nothing in there about visualization. There's nothing in there about charts. Right? The title actually speaks to the fact that you have data, and you're using that data to generate documents. Because after all, that's what web pages are. Even if they have charts on them, they're descriptions of documents. So it's mapping data to graphical objects, and these graphical objects are in the language of the web, which is to say they're elements in your browser's HTML pages, okay? And guess what? Document description languages are declarative too. They're not very pretty, but they're kind of declarative. So HTML, the language of the web, is really a tree-shaped data description of like headings and paragraphs and subparagraphs and lists and list items and things like that. And that tree is sometimes called the DOM, or the Document Object Model. It's a data structure version of an HTML page. Similarly, there's more recently, there's graphical languages that are textual that you can embed in your HTML called SVG, which stands for I forget what S stands for. V and G are vector graphics. I forget what S is. But it's just a simple text language for saying things like, this is a circle, this is a square, here's its color, here's a line, here's a curve, those kinds of things. So what we're going to do in D3 is we're going to map from data to these document standards. It's just a mapping language to give you web pages as output. Data input, web pages output. So the key ideas in D3 are awfully familiar from a database class. First of all, you can select stuff. You can select objects on the web page, right? You can also select data from sets of data. And you can join stuff. This mapping of data to the document is going to be done as a join of the data with nodes in the document tree. We're essentially going to kind of take the data, transform it, and hang it in the tree of your web page. And it's going to make it light up like a Christmas tree. Basically the general idea. Except that sometimes your web page doesn't exist yet. You got lots of data, you got nothing in your web page. You want to use the data to generate the web page. So when you try to join it, a bunch of the data's got nothing to join to. So we're going to use an outer join to capture all the stuff that didn't find anything to hang itself on. And we're going to take the results of the outer join and grow ourselves a tree out of it. All right, so you'll see how that goes. But basically, D3 is selections and outer joins. Selections, joins, and outer joins. It's like SQL heaven, except it doesn't look like it. It looks like JavaScript because very wisely they realized that their audience was not database geeks, it was web geeks. All right, before we dig into this briefly, and this is not a full-on tutorial, but briefly, some basics about HTML. So HTML pages are described in this document object model. What is a web page? It's a tree of elements, also known as tags. Elements are things like headers, paragraphs, list items, but they could also be things like spans. A span is just a bunch of text, or divs, which is just a region on the page. Okay? And you can also have web elements that are just contain tag names of your own creation, and that's legal in HTML. So it's just a tree, and each element has a name and optional attributes. So if you have a tag like foo, that's just the name of the tag, but you can give it an ID. So for any tag that you want, you can have an ID equals foo. It can have a class. And in fact, it can have anything. So you can give it any attribute name you want. ID and class happen to be standard and common. But you can make up your own attributes and stick them in there too. And so if you're ever curious about this and you've never seen it before, if you go into most web browsers, there's a web inspector or something like that you can open up. And you can navigate the tree that you're looking at up top. And you can actually usually mouse over the tree visualization in the web navigator and see which parts of the page light up. So I haven't actually set myself up to do this, but I am online. So let's see if this works. Here's your homework for homework 4. And if I do Option Command I, here's the web inspector. And this you probably can't see. Oh, and it doesn't zoom up the web inspector, unfortunately. But if we go into resources, you know what, I'm not going to be able to do this on the fly. So let's not do this now. But I encourage you to do it when you can see better. And you will need to do it for your homework. There's a picture of what it looks like. All right, so we talked a little about HTML. Let's talk a little about JavaScript. All right, JavaScript is a language that you can stick in your HTML pages. And it was originally invented to just kind of add a little bit of dynamic content to your web page. And it kind of turned into a full-blown programming environment over time. It's a very free-form language. It's arguably way too unopinionated. So you can do things in JavaScript in lots and lots of different ways, which means that everybody's JavaScript looks very idiosyncratic and weird. It doesn't, for example, have a model of objects and inheritance. It has many models of objects and inheritance that many people have made up that you can decide to borrow. This is kind of maddening, but it's very, very free-form. The syntax looks a little bit like C. It's got for loops and case statements and whiles and ifs. It's got some important functional programming capabilities. You can take function descriptions, the text of a function. You can pass them into other functions. And you can get functions that will get called back later because they're arguments that you passed in. It's dynamic typing like Python or Ruby, so there's no data types declared up front. But the built-in data types are incredibly simple. There's strings, there's numbers, no distinction between integers and floats. There's just numbers. Okay? There are arrays. There are objects. Objects are not objects. Objects are just hash maps. An object is just key value pairs in JavaScript. And there are functions, and that's kind of it. Okay? And then there's some really weird variable scoping rules, which you have to be careful with, and that hopefully Anthony has warned you about in the right places in the homework. Scoping and the stack don't work the way you're used to in JavaScript. Okay. With that introduction, what I'll tell you is that although it's kind of a free-form language, there's lots of frameworks that give it more structure for specific tasks. And D3 is one such framework. It's focused on data viz. So D3 includes code as many JavaScript. So JavaScript in general, if you have JavaScript on your page, it can access the content of your page, and it can manipulate the DOM, which is to say it can change the page. That's why it was invented. It was invented to add little values to the page dynamically, right? So it wants to be able to manipulate the page, but it can really manipulate the page. It can change the page all around. Okay, and D3 contains a library of page manipulation and page accessing routines to help it do data visualization. I'm going to not read this off, but lots of tooling that can help with JavaScript. It's a very vibrant programming environment. It's extremely popular, and people tend to like to build tools for it. So lots of good things to look at. Here's one of the key things you can do in web environments, and it's widely used in D3, which is to define selectors. So what is a selector? A selector is a declarative statement of some kind to access nodes in a particular DOM tree. So you're on a web page, and you might want to pull, say, all things with a particular tag name. Like I want to pull out all the paragraphs in this document, all the things that are tagged P. Okay? Or maybe I want to pull out all the things that are class data. Class equals, quote, data. So there's different ways you can pull things out, including by ID, by class, or by whatever attributes you made up. And I want selectors as a way to talk about, get me the set of things in the DOM tree that contain this tag name, this attribute, and so on. And these can be flat lookups, which is to say I can select, just give me back a set or an array of all of the matches. Or you can actually do nested traversal. You can say, within the body, within the first paragraph, find me all the code snippets. Right? So you can do nested lookups as well. So selectors are supported by CSS, which is the style sheets for web pages, and that's where they first came from. And I won't talk about CSS much today. They're also supported by many JavaScript packages, the most common being jQuery, which is a way to query your DOM. D3 selector syntax actually is very much like CSS. In fact, it's identical to CSS. So if you're looking for the syntax of D3 selectors, you can look for the CSS ones. Here are the selectors that are most common. If you want to pull things up by tag, you just write it down. So if you want to find all the divs, you just write down div. If you want to find an attribute of a tag, so you might have div attribute equals value, then you just write down in square brackets attribute equals value. Okay? And that red should probably be in quotes, actually. For the special attribute class, rather than writing class equals value, you can just write dot value. For the special attribute ID, rather than writing down ID equals something, you can write down hash something. Right? And if you want to walk down the tree, you just put spaces in between. So you can say H1 space, so that would be the header. So what did I say? I said within the body, so you'd say body space, first paragraph would be P space, and then you'd put down your remaining selection, parent-child. You can do conjunctions of these selections with the dot. You can do disjunctions of selections with the comma. Right? It's a little language of selections. In D3, you have two choices of how to use these selectors. You can say D3.select and then give it one of those selectors, and that'll return you the first match. So if you want the first paragraph, you'd say D3.select, quote, P, and you'd get the first paragraph. And it'll come back as an array, but it'll only have one item in it, a singleton, which is that first paragraph. If you want to get all of them, you say select all, and that'll give you an array with the ordered list of them as they appear in the document. Okay, top down. Once you have your hand on a set of elements, you can then change them in D3. You can manipulate them. You can apply an operator on the result. So you can take a selection, which is D3.selectAll something, and then you can change attributes of that selection by saying .adder, name, comma, value. And I'll show you examples of this in a minute. Or you can change the text of the selection, name, comma, value. Or you can change the style of the selection. All right? Style is a CSS thing for visual effects. And for all these things that are values, instead of putting in a value, you can put in a function. So you can have a function that later on you'll pass a value into that will compute something from that value. All right, and we'll see how that gets used. All right, so let me show you some examples. And it might take me a minute to actually set this up. I don't remember if I left my little server running. So just give me a sec. But all these examples I checked into GitHub, so you can play with them at home. These examples will illustrate the key themes of D3. Sorry. All right, and so you should be able to fire up a web server just like I did and look at these examples yourself. So the first thing we're going to look at is just styling text with D3, okay? So let's do this in the slides, and then we'll cut over to the visualization. So here's the idea. It's going to be a little script, a JavaScript script. The first thing is a select all that grabs all the paragraphs, all the P's out of the document. And then we're going to we assign that to a JavaScript variable paras, and we change its style, so the font size is to 12. We're going to change its font family to Courier, and we're going to change its color to red. Okay? And now I will show you a web page with this stuff in it. Okay? Can you guys see this? Maybe I should make it white. I forgot how to make it white. Does that change it? Nah. This one should do it, right? I know there's a menu item to do this for this window. Sorry. Default. New. No. Cancel. Go away. My apologies. Basic. Default. Close. No. All right, well, we'll just have to look at it in black. What you can hopefully see here is that I've got a web page. In the body, I've got 7 paragraphs. And in the script, it's exactly the script we just saw. So by default, these paragraphs have no style. They're just black, plain text. We're going to turn them into Courier red. Okay? Not very interesting, but that paras is going to pull all those paragraphs out, and the styles are going to modify each of them. And when we go look at this, we get that. Not too surprising. Okay? So that's very, very simple. All right, the next thing we're going to do is just look at a syntax fix. This is a little bit ugly. D3 has a much more pleasant syntax, which is method chaining. So what's happening here? Instead of having that paras variable, what we're going to do is each one of these methods returns the array of values that was passed into it as its output. So select all returns an array of P's. Style returns the same array of P's, but with the font sizes changed. So you can pass that down to the next call. All right, so this method chaining is just nested function calls where every function is returning the modified input as its output. Okay? So that makes for easier code to read and write. That's kind of nice. And the result is exactly the same. Now, where it gets interesting is when you manipulate the DOM using data. All right? Notice that the function arguments, or generally, we talked about this in your homework, when you call a function, the argument to that function is what? It's data. It's a value, right? It's a computer value. It's data. So f of x, where x is an integer, x is data, right? And a set of data can lead to a set of function calls. Select f of x from t is a way of invoking f on lots of x's. And that's pretty much what you just did for your homework 4, right? Was you used queries as a way of batch invoking a REST service. We're going to use the same idea now to build data visualizations. So in JavaScript, functions can manipulate the DOM. They can change attributes. They can change page content. So if you feed a bunch of data into something that changes the page, it'll change the page for each piece of data, which means you can get a sort of data visualization out of it. Okay, and so that's what we're going to do next. What is data in D3? It's arrays. All right, that's how D3 stores data. It could be just arrays of raw numbers, or it could be arrays of objects, which are just hash maps or tuples, right? So that's what data is in D3. And you can convert lots of things into that form, like CSV files or whatever. And so here's an example of a D3 script that's going to scale text based on data. What are we doing? Here's a data set. It's got 7 values, 10, 12, 14, 16, 18, 20, 22. We're going to select the first body element in the page. Within that body element, we'll select all the paragraphs. And then you see this call to data. What this is going to do is it's going to join the set of data in dataset to the list of DOM elements in select all. So we're now associating each one of those values with one of the paragraphs in the DOM. And then we're going to style font size, but instead of giving it a constant, we're giving it a function. That function returns what you pass in it plus the string px, which is how you talk about pixel size in JavaScript. All right? And by convention, the thing we pass in is the data that got joined, and we'll call it D. So that's going to style each one of those elements with a corresponding data value, and then we'll make it courier read. So you can imagine what this is going to look like on our web page that we had before. Right? It's got 7 paragraphs. We have 7 values. And so here's what you get out when you're done. Right? Data visualization. Not very good data visualization. But you can start to see how we can modify the outputs of things based on data. And it's just a join of the data with the DOM. And so where it gets more interesting then is when you start talking about the outer join of the data with the DOM. This joins the data set to P. And let me point out, it's joining it by array position. So the first item in data set is joined with the first thing that the selection found in the document. Right? You noticed how the fonts got bigger as you went down because these values got bigger as you went forward in the array, right? Okay, and if, yeah. All right, and this is this anonymous function that was called per datum. All right, but the basic pattern is not just a join. It was kind of handy. I had 7 data items and 7 paragraphs in the document. That doesn't always work out. So what we're going to do in general is a full outer join of data and DOM elements. The basic pattern in D3 for binding data to the DOM is you take a set of data and you full outer join it with a selection of DOM elements. By default, the join condition is on position, so the first item in the data joins with the first match in the selector. Right? But you can actually specify joins with the second argument to data that we haven't used yet, which is a function called a key function that will pull out keys from the data and keys from the DOM and do a join by key, so an equi-join, instead of a position join. So if your DOM elements are labeled with, say, IDs, and your data is tuples that have tuple IDs, you can look up the ID in each one and join them by ID. Right? This is going to be important in your homework, and there's an example of it in these examples. So great, so it's an outer join. Well, what happens when you do an outer join, a full outer join? We know this because it's a database class. I can't tell you how many web pages there are explaining this to visualization people in D3. Okay, JavaScript folks, it's not that hard. We're going to teach you about an outer join. But it's really, what's going to happen when you do an outer join, here's the data columns, here's the DOM columns. Some tuples will have both because they found a match on the join key. Some tuples will have only data and the DOM will be null. And some tuples will have only DOM elements and the data will be null. Full outer join, right? All right, we're not going to lose any data elements that have no matches. We're not going to lose any DOM elements that have no matches. We just fill them out with nulls. All right, so in D3 parlance, this is just called the, that doesn't even have a felt, much less in the ink. This part is called the update. How are we doing on time? Oh, we're almost out of time. This is the most important part. This part is called the update. These are the things that are already on the page that match with data that are going to get updated. What you just saw on the previous slide was all update. It's the inner join, right? So that's the stuff that gets updated by whatever you put after the join. This stuff here, data elements for which there's no DOM yet, is called enter. These things are like data that's entering the scene. It wasn't there before. There was no DOM element for it. But it has arrived, and it deserves to be visualized. Okay? And this stuff is called exit. Because in a data visualization, probably these elements were there because they were entered previously, but the data that generated them is now gone, and they should be made to go away somehow. So they're exiting the scene. All right? The truth is, though, there's nothing magic. So just because things are in the enter set doesn't mean you have to pay any attention to them. And just because things are in the exit set doesn't mean you have to delete them. You can do with them whatever you want. It's just an outer join where there's this set of stuff, there's this set of stuff, and there's this set of stuff. These are called enter. These are called exit. You don't have to do any enter or exit stuff with them if you don't want to. So, hello, good morning. Here it comes. Oh, this is really frustrating. Okay, it's really hard to show you example code without a screen because writing it down is going to be super duper annoying. But I'm going to do it because that's what we got to do. All right. Here is the standard pattern for enter. This is really important, and it's important for your homework. This is like a D3 pattern you see all over the place. You're going to say D3.selectAll with some selector. Okay? That's going to give you a bunch of DOM elements. And then you're going to say .data, and you're going to give it a data set, and possibly a join function, a key function. Okay? And that's going to associate each data item with a selected element or tag. But for those things that are entering, we want to give them some DOM elements to go on, right? This data that doesn't have any DOM elements yet. So we're going to say .enter. And what that's going to do is subselect to the set of items in the data that did not find a match. So it's just saying, find me the things in the left side of the left outer join that don't have a match. And usually we outdent this a little bit because instead of returning its inputs, it's returning actually something different, which is a subset of its inputs. The enter returns only the things that didn't match. All right? And then for each one of the things that didn't match, we'll append to the DOM a new thing like this. So everything that's entered is going to get the thing we were searching for. So if we were looking for P's, you associate all the existing P's with data. That comes from the update. And then for all the enter things that didn't have a matching P, we add a P to the DOM. So now there's a paragraph for every data item. Make sense? This is super standard. This is how you make sure that all your data gets represented the same. You find the ones that already have matches, you join them up, and then you add matches for the ones that didn't have that are the same as the ones you were looking for. So this is a little weird because you might start with a web page, and this is the thing that they always use in the tutorial, where what you're searching for are things that are circles in a visualization. But there are no circles in the visualization. The visualization hasn't even started. That's okay, because you append them down here. So the first time you call this, nothing matches here, everything's here. But in future, when the page is updated, all the old stuff stays matched and new stuff gets added when you add new data. Okay, so this is in the slides. I apologize they're not up on the screen. You also often, another standard pattern you'll see in your applications for dealing with exit, which usually goes the next line after that, d3.selectAll, the same selectAll, let's say circle, .data, data set, .exit. So these are the things that are DOM elements that found no matching data, .remove. And that takes them out of the DOM. So this is the standard enter and exit patterns. Okay? And that is enough to make you dangerous for your homework. All right? What we go through in the rest of the slides, and the examples are in GitHub. We'll do them on Thursday, but if you want to look ahead, is we show how to go from styling text to building bar charts. And then from building bar charts to building SVG things that are much more interesting. And we don't even do anything in the examples that's that sophisticated, but man, you should see some of the stuff people build with D3. It's just beautiful and very sophisticated. So you'll do something actually pretty nice in your homework. We'll finish this up on Thursday. I'd encourage you to start looking at the homework now, though. I did a bunch of it over the last couple of days. It takes some time, so especially if you don't know the tool chain. One more thing. Anthony's going to host a D3 on JavaScript tutorial session tomorrow night. We're just waiting to get a room, right? TBA. So watch Piazza for an announcement about a tutorial session. Take care.